All right, this is our third KCS talk for this semester. And this is our speaker, Mr. Evan Damron from Center for Applied Artificial Intelligence. I believe you're with Cody, right?
Yes, sir.
Okay. And the title of his speak is an LLM-Driven Robotic Healthcare Assistant with Multi-Modal Environmental Sensing. All right. So this is a 50 minutes talk. So make sure that stop at 12:50. All right. So let's welcome the speaker. Okay.
All right. Thank you for the introduction. I'll go ahead and jump into it. Okay. So first, I want to talk about some of the differences between the robots of science fiction, like C-3PO and R2-D2 from Star Wars, and the robots we have in mass today. The main difference is how generalized the robots are. So what we have today is robots that are very domain specific. They're good at one specific task, but can't really deviate from that. So for example, the robotic arm in the factory can do what it does really well, but if you put it in a different factory, then it would fail completely. So they don't have any common sense or general knowledge of the world. Everything is just programmed into the robot. And then they also have limited autonomy. So the most impressive robots we see typically aren't totally autonomous. So even these Starship robots that deliver food on campus are not fully autonomous. They're mostly autonomous, but then whenever they reach a hard decision point or a confusing scenario, they're overridden by a remote controller. And then also the communication with robots, especially communication with humans, is lacking right now. That field is called human-robot interaction. But with the advent of large language models, it's definitely possible to improve that aspect of it, and that's a large focus of this talk. Okay, so I'm going to be talking about background on the traditional way that robotics are programmed, which is called rule-based systems. And then I'll introduce large language models, and then briefly talk about some of the healthcare applications of this. And then the largest section of this talk is going to be a case study of using large language models in robotics in a healthcare context with an example of that, and then I'll talk briefly about the future work and challenges. Okay, so robotics up until very recently have been rule-based, which means they're deterministic. They're always going to do the same thing given the same information. These follow an if-then style of rules. So, for example, a robotic arm in a factory, it might have a rule where if it sees a certain screw, then it will loosen it if it's disassembling something. And you could implement this however you want. You could do 1,000 Boolean variables if you want to, but that's going to be impossible to scale and just harder to manage. So there's a couple common architectures that are used to implement this type of robot. One of them being state machines. State machines are a model of computation that describes a system as a set of states and the transitions between them. And this helps give a structure to the flow of the robot. For example, with a disassembling robotic arm, you might have one state for each step in the process, and then after that step is completed, you transition to the next state. So these are pretty elegant and simple. It's easy to visualize what's going on. But the problem is these scale very poorly. As you add capabilities, you have to add states, and the number of states blows up to an unmanageable level as the robot gets more complex. So another alternative to that is behavior trees. So these scale better than the state machines, but they still ultimately have the same problems that you have to define every single rule in the system and that they do not scale very well. So like I said, all the rules in these systems must be implemented by a programmer. They have no common sense reasoning or general idea of what's going on in the world. The code base gets much more complex as your application adds new features. But these aren't completely obsolete. These are still the best choice in a lot of different applications. So, for example, a robotic arm like the example I used, a state machine would be a perfect way to implement that because you don't need it to adapt to unknown scenarios or unpredictable environments. Same thing with automated guided vehicles. Amazon has these employed in its factories using rule-based programming, and that works well because those factories are very predictable. They're a well-oiled machine, and you can make those rules. When you start dealing with humans, though, that quickly breaks down because human interaction by nature is very unpredictable and ambiguous a lot of the time. So if you try to design a rule-based system to handle a conversation, it just would not work. And even if you could implement all those rules, it would not appear natural. So that brings us to large language models, which excel at dealing with humans and human interaction. So I'm sure everyone's familiar with them at this point, but they've been trained on LLMs are massive neural networks that are trained on massive data sets of text. And through that process, they they develop general reasoning and intelligent features. So one key feature it's important to grasp of LLMs is that they're stateless. So that means that the output of a certain input is completely dependent on that input. So they have no memory. They don't have any history of past interactions. So anytime you query an LLM and it seems to remember details about you or remember things even from previous chats in your same conversation with a chatbot, that means that somewhere a programmer has put in effort to make it appear that way. And the way you do that is pass all the information from all the interactions to the LLM at the same time. So what I'm trying to get across with this figure here is that LLMs are not synonymous with chatbots. Instead, chatbots are an application built around an LLM. And you could build several different kinds of applications. So you can use Copilot, Windows Copilot, which can take actions for you, can send emails, edit documents, things like that. Or Cursor even, which is an AI code editor. And they're all built around the stateless LLM backend. So the process of giving an LLM a memory or remembering past things you've said to it is called context management. Context is the amount of information you pass to the language model at one query. And if you have too much context, you can give the model a lot of irrelevant information and it can focus on that and then it will reduce performance. But if you don't give enough, the language model isn't magic, so it can't answer a question when it doesn't have the information you need to answer that question. So one of the fundamental challenges of creating LLM applications is managing this context. And then the other big challenge is how you prompt the LLM. If you ask an LLM the same question but phrase it two different ways, one of those might perform significantly better than the other. So that's something that requires tuning. All right, so tool calling is the basis of how you turn language models just from chatbots to agents. It enables an LLM to analyze your intent and to output a structured output based on tool descriptions that you've given it. So a good way that I think to understand this is first seeing the bad way to do this, which is just by prompting. So if you want an LLM application that can give the current time, the language model doesn't know the current time. It has to rely on that data from some external source. So you can tell it to, in your prompt, to say, if the user asks for the current time, then give this structured output, and then have a manual check. If you receive that output, return the time instead of the LLM's response. So this way of doing it does not scale well. As soon as you have several tools or several parameters in these tools, it's going to break down and not perform very well. So to get around this, the large language model companies have fine-tuned their LLMs and by providing millions of examples of structured tool calls and providing a way to pass these tool calls in a format that the language model accepts. And then by doing that, you can have a large larger amount of tools that are more complicated. So we'll see an example of that later on. And then reasoning, instead of fine-tuning an LLM on basic reasoning, it's an emergent property by being trained on lots of technical papers or question and answers in the internet. LLMs develop this basic reasoning. They're able to solve problems even if all the information isn't there. But you can improve the reasoning by telling the language model to think step by step, which is called chain of thought prompting, and leads the language model to output a long thought process and then eventually say the answer. And then using this information, companies that make large language models have actually decoupled the reasoning step and the answering step. So they have this chain of thought prompting almost built into the response, and that's achieved by fine-tuning the LLM on millions of training examples. And yeah, reasoning models have been shown to do much better at tasks that require complex problem solving. Okay, so with all that background out of the way, now I want to introduce the Temi robot. So Temi's a commercially available robot built on an Android platform. So you can build Android apps on Temi using Java or Kotlin. And right now we've got Temi set up as a greeter, almost a secretary in our office. So when you approach Temi, it'll interact with you, you can talk to it, and it can follow commands. It has basic knowledge about our office and the locations of different people. And oh yeah, so with this being a commercially available robot, a lot of the low-level navigation or object avoidance features are built in and exposed through an SDK. So this project focuses more on the high-level reasoning and then translating that into SDK calls like move to this location or things like that. So yeah, some key features of Temi is that it streams real-time information to a server, and it's tailored to be a healthcare assistant robot, so it's got a lot of environmental sensing features that are specific to healthcare. For example, fall detection via computer vision to detect like if a nursing home or hospital patient is on the ground and alert the staff. Also smell detection via machine learning. And the smell detection is a proof of concept for detecting if there's any smells indicating a hygiene issue in a hospital, or if temperature or humidity is out of whack, and you can get that corrected. And then the main focus of this presentation is, since in this context Temi would need to, or any robot would need to interact with patients and with staff, is to be able to hold natural conversations and then accept ambiguous natural language commands. So that's the focus, but I want to briefly talk about the fall detection and smell sensing. So the way we did the fall detection is using a pre-trained you only look once, YOLO, pose estimation model. So this is able to pinpoint the different points on a human form, so it can get your head, elbows, hands, and has all those points from an image. And then we have 3 different models that are simple using this pose estimation, and these models each have their strength and weakness, and if they all agree that they've detected a fall, then Temi's going to report a fall. So the first one's just the bounding box aspect ratio. If a person's bounding box is more wide than it is tall, then there's a good chance they're horizontal. That can fail if, say, Temi only catches the top half of a person, but that's corrected by the other models. The other one is the pose estimation key point analysis. That measures the angle from like your belly button to your head, and if it's mostly a horizontal angle, then it's probably a fall, but that could fail if somebody's maybe bent over or something like that. And then the last one is the position in the frame. If most of the person's body is on the bottom half of the frame of the image, then it's most likely a fall. And then if these models agree, we can detect a fall. And then smell detection is an active area of research. So we've equipped Temi with the Smart Nanotube Smell Inspector, which measures like carbon nanotube variants, and we've used self-supervised learning techniques to achieve 86.5% accuracy when detecting ammonia in an unseen environment. But there's a lot of challenges with the smell detection. Like, for example, the sensor quality degrades over time the longer it's being used, and the readings vary from month to month. So it seems that you would need to retrain or account for this variance. But with certain things, retraining would be very expensive because you have to get new labels for new data with the new version of the sensor that's degraded. And then also, there's not very much external data. Big reason for that is that people aren't really in agreement on what to measure for smell sensing. So you can, there are different smell data sets out there, but they each measure different things, so it's hard to combine those to create a large data set. But that seems to be changing. There's more efforts recently to make that agreement and make a large-scale data set so that soon, hopefully, a foundational model could be trained on this type of data, and hopefully that could get around some of the aspects like sensor degradation and also environmental factors, because another big challenge is that if you measure ammonia inside and then measure it outside, it's going to look very differently, even though it's mostly the same substance, so the environment plays a big factor. Okay, so Temi streams all this data, and we've got a nice dashboard on our Office TV. So here's all the 4 computer vision models, and then here's Temi's location on our Office suite map. And we plot the smell classification as green dots as ambient air, and then if it detects ammonia, it'll be red dots. We've got some metrics, and then a plot of the smell data. So that's the environmental sensing aspect. Now let's talk about the human-robot interaction. So our first approach did not include any large language models. It was just a basic flow chart almost. It used a state machine to manage the role-based system. So the way this one worked is if you approached Temi, it would use a built-in computer vision detection model and then identify that you were there, and it would simply ask you, do you want to go visit somebody in the office, or can I help you find someone? And then if you said yes, it would display a list of all the people. You could select who you want to see, and Temi would take you there and move back. So it was very limited on what it could do when interacting with people. And it had 9 states and a lot of transitions in the state machine to manage everything in this, all the rules. And after we integrated the large language model, we combined all the human-robot interaction into one state, the LLM control state down here. So as soon as a person's detected, we go here, and then as soon as our action queue is empty, we move to entrance, and we're back to detecting. So by giving control over to a large language model, it simplified the code a lot. It makes it easier to add new functions because all you have to do is tune your prompts and tune your tools. And it's also a much simpler code base and easier. It gives a boost in capabilities. So the LLM can do more general tasks rather than just ask a yes or no question and listen for yes or no. So now looking inside the LLM control state, the first thing we did was try to implement this with one big large language model to handle everything. And that did not work. It could maybe plan the actions that you asked it to do, but then it wouldn't talk to you, and we wanted to make something that appears to speak naturally, but also do what you tell it to do. So we split out the 2 parts of the robot brain into 2. There's the talker LLM, which handles the interaction, and then the planner language model that handles action planning. So the talker LLM uses a tool call to trigger whenever the conversation has come to an end, conversation over, and that can be called in 2 scenarios. One, if Temi starts a conversation and it just naturally fizzles out, like a person says okay or something like that, Temi's not going to keep that going on unending. And then also, if somebody gives Temi a direct command, then the language model will recognize that, trigger the tool call, and then move on to the planner. For the talker language model, we use Llama 3, I think with 8 billion parameters. And then the planner language model, we use a larger reasoning model. We use DeepSeek R1 for this. And this takes as input the action history, everything that Temi's done and every interaction it's had, and then creates a step-by-step list of actions for Temi to follow next. The two actions that Temi has available to him are move to a predefined location and then speak a message. And that message has a listen parameter. So if you speak a message and listen is set to true, then it's going to use the talker LLM for that interaction, and it's going to handle that with the language model. If you speak a message with the listen parameter set to false, then Temi's just going to speak it and move on to the next action without waiting for a response. So I want to talk briefly about the prompts of these language models, how we do that. So prompts have two aspects: a system prompt, which is the overall goal of the language model, pretty much, and the user prompt, which is the interaction. So for ChatGPT, the system prompt might be, you are a helpful assistant, and then the user prompt is whatever you ask it. So for the system prompt for this, we embody the language model. We tell it it's acting as Temi, so that way if you ask Temi, what are you, it won't just say, I'm an AI assistant, it'll say, I'm the Temi robot. And then we also define the conversation over tool and when to call it. That's to reinforce the tool call, but the important part of the tool call is you provide it in the JSON request to the language model. You define it programmatically. You say a description of the tool, when to call it, and then you also provide the parameters. So the conversation over tool call has a message parameter, so Temi can speak even after he's ended the conversation, and we require Temi to use that message parameter. So this uses the fine-tuned tool calling capability of the language model. And then, yeah, for the user prompt for the talker LLM, that's just whatever you speak to Temi. So now the planner system prompt for the reasoning model gives the language model general instructions, embodies the LLM like previously as an expert planner for the Temi robot that generates a sequence of actions, and then we define those actions and enforce that they're given to us in a structured output. So the reason we need these to be in a structured output is because we're eventually going to take these results and turn it into executable actions, turn it into code. So if it just gives a natural language answer, like say the message, lunch is ready, and wait for a response, then that's hard to programmatically turn into code. And we can enforce this with few-shot examples, which is giving a couple examples of each action in the format we request. And then at the end of the system prompt, we just restate the general instructions. So the planner user prompt is built over time as Temi interacts with the world. So it's kind of a stencil. Parts of it stay the same, parts of it change. So the initial line is, here's a log of past events. That's always going to be there. And then as Temi does things, that log will be built out as people interact with Temi and as Temi takes actions. And then we give the planner Temi's current location. And that line is always there, but the location changes, obviously. And then at the end, we always tell the planner to create a full action plan, step by step, based on the sequence of past events. So this is best understood with an example. So we'll say that I approach Temi in the office, and it detects that I'm there, and it triggers the interaction. And this is going to use the talker LLM. So we're going to inject this, how can I help you, into the context of that language model. And whenever I answer, I'll say, can you ask Sam what time the meeting is? So this is a direct command. So the talker LLM will trigger the conversation over tool call. And the message parameter of that tool call will be sure thing. So Temi will speak that command, and then the action, the speak action that the initial interaction is completed. So after the action completes, we construct a natural language description of that action to put into the planner's user prompts, to put into that section that we build out in the planner. So for this example, it's Temi had the following conversation, Evan said this, or Temi said this, Evan said this, Temi said this. And then from there, the planner is going to read that in the context of the entire user prompt and decide on the next sequence of actions. So for this interaction, we'll say the planner decided to make the plan, move to Sam, speak what time the meeting is with the listen set to true, and then move to Evan and speak the meeting is at 2 p.m. with listen set to false. So the issue with that, and this comes up a lot, is the planner is greedy. It wants to solve the problem immediately, so it pretty much tries to generate a full action plan every time. But we know that you can't plan past the time where we ask Sam what time the meeting is, because we don't have any of the information we would need. So because of that, we have the rule that whenever we use a speak action with the listen parameter set to true, we're going to replan after that based on what that conversation entailed. So the model hallucinates this, but it's not a big deal because we're never going to get to this action anyway. So now the planner's populated an action queue. We're going to go to the next action, which is move to Sam, and then we're going to start the speak action of what time is the meeting. So there Temi moves to Sam, asks, hello Sam, what time is the meeting? Sam says, or I should mention too, Temi moved to Sam, so we're going to add to the planner's user prompt the natural language description of that. Temi moved to Sam. Anyway, back to the interaction. Sam says, I don't know, it's Cody's meeting. So this is a ambiguous response. He didn't give a direct command to go to Cody's office and ask him, but the planner is able to, or the talker is able to recognize that the conversation that was started has naturally ended. Temi asked a question, Temi got its answered, so now it's going to call the conversation over tool and say, okay, I'll ask Cody, and then we'll feed that whole history to the planner, and the planner is able to realize, okay, we need to know what time the meeting is. Cody knows what time the meeting is, so we'll move to Cody and speak when's the meeting. And with the listen set to true, we've erased the previous action queue, but we'll say the planner hallucinated this new meeting time again. Now it's 4 p.m. instead of 2 p.m., but oh well, we're never going to get there. We add the conversation history to the user prompt, and then we replan after this tool call. So we'll say Temi moves to Cody and starts the speak action of when's the meeting. So there we go. Temi asks, when is the meeting? Cody replies, it's at 3:30. So this is the same example as before. It's not a direct command, but it's the logical ending of the conversation. So Temi's going to call the tool. Okay, I'll tell Evan. And we're going to replan, update the action queue with logically grounded actions this time. Move to Evan, speak. The message is at 3:30 p.m. Listen false. There's nothing to wait for a response for. And this is a small example of common sense reasoning. Cody never said it's at 3:30 p.m. It could have been at 3:30 a.m., but the language model knows it's working in the context of an office, so it's safe to assume we're talking about 3 p.m. here, p.m. here. So we'll move to Evan, speak the message, and at this point the action queue is empty, so this interaction is over. And we can erase the user prompt of the planner, we can reset that, and that's when we clear the context for this application. So at this point, Temi's going to transition out of the LLM control state and move back to the entrance and start from the beginning. Okay, so there's some key concepts in this application that apply to similar applications. For one, you can't get rid of state machines and role-based systems altogether. It wouldn't make any sense to use a language model for something that you could do in one line of code. And for example here, we start at the home base, and then if the time's between 9 a.m. and 5 p.m., we start moving to the entrance. So if you tried to use a language model for that, it would probably work, but it'd just be dumb, it would be wasteful, it doesn't make sense to do. Another concept is dynamically replanning. So in our application, we have a pretty simple replanning rule. Whenever you talk to somebody, you probably got new information, so you're going to replan. But that is a concept throughout any application like this, because in the real world, you don't have all the information ahead of time, so you have to know when things change or new information presents itself, and then know to replan. Then another concept is separating duties out for different models. You don't want to use, at least in the current state, you don't want to use one large model with the same prompts for everything. It's just not going to work very well. And even if you had a model powerful enough to do that, it is probably wasteful. You're better off using smaller models that are capable of doing individual tasks and making an ensemble of those. So I want to talk a little bit about the future directions of this. So NVIDIA has kind of positioned itself as the leader in physical or embodied AI. This quote from their CEO, Jensen Huang, says, "We built the world for ourselves. Using data from humans will make robots the most productive they can be." So that's part of their argument that the new form of robotics will be humanoid. And this quote addresses two aspects of that. For one, the world, all the infrastructure we've built is designed for human beings, so we know that the human form is capable of navigating it. And then also, a big challenge in this field is getting data to train on. And if you create a new robot that's shape and wheels everywhere that no one's ever seen before, you have to generate all that training data yourself. But if you use humans, you can use videos of humans, and there's a lot of data related to that already existing. So to build up to that, you need to add more modalities to the model's world model. The world model is just what the model uses to make decisions, how it takes the experience of the world and feeds it to a model to make a decision based off of that. So in the Temi application, right now it's a text-only world model. We just have a description of events, and then the model uses that and its common sense reasoning to make a decision. Tesla's self-driving uses a vision-only world model with their Tesla Vision, just 8 camera feeds into a neural network, and a self-driving car is essentially a robot. And then NVIDIA is expanding that for their foundational humanoid robot project to a text, vision, and state world model. So that uses uses natural language commands and large language models combined with vision, combined with the robot state, which is like the position of its body, the angle of its joints and how it's standing, things like that, to get an understanding of the world. So the obvious next task for this type of project is to expand the world model to include more modalities. So for Temi, the next step is vision. Using vision language models, you can use the similar architecture to what we have now, where we have a planner that takes in maybe a picture of the world and the text description and then works with that. Because the text-only model has limitations, we have to make certain assumptions. So for example, if Temi's at the location of Sam, it's going to think it's talking to Sam. It doesn't use vision to detect that. So, but this is a concept that's widely used in widely going to become used in robotics, adding more modalities to truly get to a human level of world understanding. You would need to add vision. You could add smell to the actual decision-making process instead of an external environmental sensor. You could use tactile sensors to give the model an understanding of how things feel rather than just vision and the state knowledge. Google put out a blog post earlier this summer talking about Gemini 2.5 Pro's ability to do image understanding, like its ability to understand images based on text prompts. So for this example, Gemini 2.5 Pro was based only on a text prompt, able to create a bounding box and a segmentation mask around a spill. And in the past, that's something you would have to do with a custom model. You would have to train your own computer vision model to detect spills and create the area to wipe with a robot. But now these things are becoming more built in, and just general world understanding is the way to make robotics applications that are much smarter, much faster. So, and then another big challenge is distilling models down into a size that can be run locally. So right now, Temi could give you a history lecture if you wanted it to, because it uses the base large language model, but that's wasteful. You don't need that in the Temi robot. So if you can find a way to distill the model down to a size that's easy to run locally, you don't have to be dependent on cloud providers, which is very expensive and adds latency. And you can also have the same functionality that you need. So that's all I've got. Any questions?
So the speech recognition stuff, that's all part of the Temi platform?
Yes.
It's the low-level stuff? And how reliable is that?
It's okay. A lot of the times it'll mistranslate, but we've seen DeepSeek able to get around that.
I mean, so it renders it to text and then you feed the text into the LLM?
Yes, yeah. So you're right, another modality that would be good to add is raw audio rather than translating the text.
In the LLM, like in your example, you said, can you tell me what time the meeting is? Which you said it's a command, it's really a question. The answer could be yes or no, right? But somehow it recognized that as a command.
Yeah, I think it was, can you ask Cody, or ask Sam?
Well, it was can you, right?
You're right, yeah. So I guess it should be.
Is that a real example?
Will you? Yeah, that example works. I don't know if that exact phrasing works, but maybe you do have to be more specific.
So I know you said that it kind of sometimes hallucinates the second step of the speak action plan, right? Have you ever noticed it hallucinating even the first step? You know, when you ask that question, does it, I don't know, just make up that actually Cody isn't in the office or something like that? Anything along the lines of that?
Yeah, it can happen the more abstract things you ask it, but typically for an example like that, it's pretty straightforward and it doesn't start losing information or making things up until farther down the chain. But usually the initial action is almost always correct, and then as it gets further down the chain, it breaks down a little bit.
Got it. And so let's say that it goes to the office and Sam isn't in the office, so it says a question, but it listen is true, but there's nothing it's receiving.
Yeah.
So what does it do then?
So at that point, it has a timer where it's listening to Sam, and then it'll give to the planner a message, Sam didn't answer the question, and then the planner will decide what to do next. So in that case, it would probably move back to Evan and say, I asked Sam, but he didn't say anything.
Got it. So I think you might have mentioned this, but I guess how does the, like you just said, it will say Sam didn't say anything. How exactly is that translation happening? Is that also kind of like LLM? You will feed the context into it, and then it will generate a natural language?
No, those are fixed for each action. So the SDK for Temi provides methods when you send a command like move, you can tell when that command completes or if it fails, and then based on that, we use just we automatically just construct the textual description of that action.
Got it. Thank you.
Yeah, thank you.
Questions? I have a question.
Yeah.
do you use since your application is basically for medical area, right? So how do you choose your data and the tools?
What do you mean by the tools?
No,
Like
each-
the vision and smell, or?
Well, each AI system has data set to train the system, right? And you also has a toolbox, to determine how should each application be handled, okay? So do you have can you choose your own data and tool for your system, or those things go with the system?
Yeah, so right now we use just the base version of like Llama and DeepSeek, but it's definitely possible through adapters or RAG to give those language models like certain understanding of your specific environment. So you could easily sub out that model with a fine-tuned model that knows about like your hospital or something like that. So if a patient asked what time is lunch, it would know the answer to that. So right now it's just the base version, but it could be trained on a specific setting.
So I think what was being asked is what's built into the box versus what was chosen and used separately. So Dr. Calvert said, was the language interpretation, transcription, that's already been. But vision models, the language models, the smell sensors, the streaming feeds of that data were things that were created independently. So you would be able to choose specifically what understanding model, what vision model, what data that you would train that system on. So you're using a platform that essentially knows how to move around and knows how to get information in for voice and how to produce text-to-speech, speech-to-text, and has a plan as far as being able to control, and it's pretty much it. The rest of it is just a software development kit that then Evan and others have had to make these other systems do.
You said that you use Llama 2 or Llama 3?
Llama 3.
Llama 3.
Yeah.
That's 3, right?
Frank, you're holding the mic so you can get it on the recording.
Oh, all right, sorry. So Llama 3, is that free?
Yes, yeah. Both models we use, Llama 3 and DeepSeek R1, are open source.
All right.
Yeah.
I didn't know that you can use Llama 3 for free.
Yeah.
All right, good. Yeah. Any other questions? Well, just thank the speaker again. And before you leave, please sign in. We have a piece of paper there, okay? Please sign in. We need that list. Thank you very much.